Okay, folks, I already have 2 minutes past, so I'm going to go ahead and get started. I don't think I have anything new in the way of logistics or housekeeping things to discuss. Do you have any questions, comments, or concerns for me before we get started with physics for the day?
It looks like it's spelled a Born approximation, but I've been writing Bohr approximation. Is this, what is the spelling?
Yeah, so it is Born approximation, B-O-R-N, named after the physicist Max Born.
Oh, I've been writing the wrong name. Okay, thank you.
Sure. Also called the Born-Oppenheimer approximation. Of course, after Robert Oppenheimer. Looks out from Spain. Any other questions? Okay, if not, then let's briefly recap what we did last time. We've been discussing scattering theory, and so we spent a significant amount of time last class discussing how to think about scattering theory in 3 dimensions based on what we did last semester with scattering in 1 dimension. In 1 dimension, it was really simple because there were literally only 2 directions. There was left and right, and that was it. In 3 dimensions, the problem is much more sophisticated because you need to describe the propagation of probability in any direction, which leads us to formulate the boundary value problem in space as a combination of incoming probability in the form of an incoming plane wave versus an outgoing spherical wave. So the general approach is to solve your time-independent Schrodinger equation as a boundary value problem, subject to the asymptotics as r goes to infinity with an incoming plane wave and a scattered wave, which is some spherical wave. If we pull out the overall normalization of the incoming plane wave, which is overall arbitrary, then the incoming plane wave has the form e to the I k dot r. This k is the k incoming or k incident, describing the direction of propagation of the scattering particle, the one that's coming in. Typically, we choose this to be pointing along the z-axis. The outgoing probability goes out in the form of a spherical wave, e to the I k r over r, and the overall modulation of that is what we call the scattering amplitude f. F encodes both the overall amplitude for scattering based on how big f is, and the directional information about where the probability goes. So the overall probability is flowing out radially, but it doesn't have to be flowing out equally in every direction. So this is a function of theta and phi. And we showed based on the probability current in compared to the probability current out, that this leads to a flow of probability expressed as a cross-section. Remember that that's a rate divided by incoming current so that you can compare one measurement versus another measurement with different beams. We showed that the cross-section is simply the scattering amplitude squared. So if you find the scattering amplitude, you square it, you immediately get the cross-section, which is your observable. How do you calculate the scattering amplitude? If this is sort of the general expression, if you know f, then you know everything. How do I find f? The first and the simplest way that we did it was by using Fermi's golden rule for the time-independent case. We started off with Fermi's golden rule, 2 pi over h bar, transition matrix element of the potential V squared, energy-conserving delta function. And we used that expression for the transition rate, and we turned it into the transition cross-section. And this is what we got, that the cross-section is proportional to the absolute value squared. There's some dimensionful coefficients, and then the most important part is that you have something which is proportional to the Fourier transform of the potential. Integral d3r e to the minus iq dot r v of r. And just to emphasize, this is within the Born approximation. Born approximation is synonymous with first-order perturbation theory. Usually it's referred to as the Born approximation in scattering theory, but it means the same thing. So this is the lowest order contribution to the cross-section in V. And in principle, this thing can be corrected at higher orders in V. So if this is my expression for the cross-section, I compare it to the cross-section written as the scattering amplitude squared. So clearly this thing inside the absolute value brackets must be the scattering amplitude. And kind of bizarrely, we introduced a minus sign here. We'll see hopefully today where that minus sign comes from more rigorously. But ultimately, it doesn't matter because you square it anyway to get the probability. This is expressed in terms of the momentum transfer vector Q. So h bar Q is defined to be the difference between the final outgoing momentum and the incoming momentum. And that means that Q squared magnitude is related to the scattering angle theta. So if I take this formula and I plug it in, I get Pf squared, Pi squared. Both of them are equal because the particle has the same kinetic energy going out for elastic scattering. And so it's just proportional to 1 minus cosine theta. And after you shuffle around your trig identities, you can write it as h bar squared Q squared is proportional to sine squared theta over 2. You can write this either in terms of the momentum or the total energy of the collision. So this is my picture of scattering theory at lowest order in the Born approximation. What this formula tells me is that whatever potential I've got that I'm scattering off of, in the Born approximation, all I really do is I take that potential V of R and I decompose it into its Fourier modes. Each one of those Fourier modes carries a definite amount of momentum, h bar q. So if I know that my potential is made up of a specific superposition of momentum states, then my overall scattering probability is the sum of the probability to absorb one of those modes. So it's an integral or a sum over all Fourier modes compatible with the final state kinematics that take up momentum h bar q and take you from P initial to P final. So this is what it looks like in the Born approximation, but it's not very clear from this discussion how do you go beyond that. So what I would like to do today is first let's work out very carefully a specific illustrative example of how to do this in practice with the Yukawa potential. And then let's discuss how to go beyond the lowest order in perturbation theory. And that will ultimately have us construct a diagrammatic representation just like this, but more generally. This is the origin of Feynman rules in relativistic quantum field theory. But a simpler version of the Feynman rules works equally well for us here in non-relativistic scattering quantum mechanics. Okay, any questions about the stuff that we discussed last time? Okay, if not, then let's dive in and work out a specific example. All right, so the specific example that I'd like to discuss is the Yukawa potential. V of R is an exponential e to the minus mu r divided by r. In terms of practical application, let me give myself a coupling constant here, some g to control the strength of it. In terms of practical application, all you really need to do is if somebody gives you a potential, you Fourier transform it, you plug it in, you're done. But I want to take some time and discuss the physics of the Yukawa potential to help us better understand what it's telling us. The Yukawa potential is closely related to the familiar Coulomb potential. Of course, the Coulomb potential is V of R is proportional to 1 over R, with maybe some coupling constant in front. So the Coulomb potential is basically the case of the Yukawa potential if this constant mu goes to 0. Equals Yukawa with mu equals 0. So what is this thing? The Coulomb potential we know very well. This is the electromagnetic attraction between positive and negative charges. So the Coulomb potential describes the interaction between a positive and negative charge mediated by an electromagnetic wave. This is described by the photon. In contrast, the Yukawa potential describes an effective interaction in nuclear physics. It's a pretty general form of a potential, but to give you some physical example to wrap your head around, this describes the effective attraction between, let's say, a proton and a neutron that are being held together to bind into a nucleus. This thing is mediated by the exchange of a pion. It looks very similar, but the crucial difference is that the pion has a characteristic mass. The mass of the pion, mc squared, is approximately 140 MeV. Don't quote me on the number, but it's somewhere in that ballpark. The photon, on the other hand, is exactly massless. And this mass scale associated with the pion or the photon is equivalent to this scale mu. If I take this scale mu, I can write something like mu r is MC squared R over H bar C. And I guess I got to put an H bar upstairs for this. Right, so this would be energy times length. Energy times length divided by H bar C, which has units of energy and length. So this mu up to factors of H bar and C, mu is equivalent to the mass of the particle that's mediating this potential. So the difference between the Yukawa potential and the Coulomb potential is that the Coulomb potential is just a pure 1 over R. The Coulomb potential has an exponential weighting factor on it that changes the long distance behavior. I spent some time this morning plotting some functions like this in Mathematica, and I put them up on Canvas. Let me share screen for a second. You guys seeing this?
Yes.
Okay. So we'll talk about these other plots in a minute. This one in the top left is what I want you to see here. This is just the plot of the Yukawa potential here in black as a function of mu r compared to the Coulomb potential. You see that both kinds of potentials have the same short distance behavior. The difference is in the long distance behavior, that the Yukawa potential dies quickly to 0 because of that exponential damping. The Coulomb potential only goes to 0 very slowly. And that shows up in its Fourier transform and in the cross-section. So we'll come back to this. But the critical difference is that the Yukawa potential has a range associated with it. That the exponential damping sort of kills off the potential at a characteristic distance. In these units, it's around 1. Whereas the Coulomb potential has a very long range tail. So in terms of physics, this is associated with the fact that the Coulomb potential is a long range interaction. Because the photon is massless, it can travel very, very far distances. But because the pion has a mass, the Yukawa potential is limited to a particular range. So finite range. And for the mass of the pion, this means that the range is approximately 1 femtometer, which, not accidentally, is the characteristic size of the nucleus. So if you have a neutron that's more than a femtometer away from the proton, they basically don't see each other. And there's only an attractive force within this finite range. That is the physics of the Yukawa potential. So we will actually, in one fell swoop, find the scattering cross-section for the Yukawa potential and the Coulomb potential, because we can do it for the Yukawa potential, and then we can take mu to 0. And then we will also get for free the answer for the Coulomb potential. So let's work it out in practice. If somebody on the comprehensive exam, for instance, gives you something like this, what do you do with it? The first thing you do is you calculate the scattering amplitude. F equals, you have some coefficients out front. Since I botched them before, I have now committed them to memory. It is 1 over 2 pi h bar squared with a minus sign. Integral d3r, e to the minus I q dot r v of r. This is, of course, just the Fourier transform. So if I plug in these factors, I have minus mg 2 pi h bar squared integral d3r e to the minus I q dot r vector e to the minus mu r magnitude divided by r. So mathematically, the only thing you have to do is take the Fourier transform. Depending on the function, that could be easy or it could be hard. This one is not too bad. So let's open up this integration. I have a vector product here that depends on the angle. This stuff is a scalar. So this thing is minus mg over 2 pi h bar squared. The three-dimensional measure in spherical coordinates is d2r times r squared going 0 to infinity. Integral d theta sine theta, that is much more convenient to write d cosine theta from -1 to +1. Just to remind you that this is equal to d theta times sine theta with theta going 0 to pi. And then integral over the azimuthal angle d phi from 0 to 2 pi. Now, the reason for breaking this out into cosine theta is I can call that dot product qr cosine theta. So I have e to the minus I, magnitude q, magnitude r, cosine theta, e to the minus mu, magnitude r divided by r. Now we can start tackling the integration. The phi integral is obviously trivial. This one just gives me a factor of 2 pi. And happily, that 2 pi exactly kills that 2 pi. The cosine theta integration is non-trivial because it couples to the angle in the exponent of the Fourier transform. So let's tackle that. That one is also not hard. So what I get is integral d cosine theta from -1 to +1, e to the I q minus I q r cosine theta. So I integrate the exponential and I get 1 over minus I q r. The exponential evaluated at the upper limit, which is e to the minus I q r, minus evaluated at the lower limit, which is e to the plus I q r. So if I plug all of this stuff back in, what I have is F equals minus mg over h bar squared. Let me pull out the minus IQ. And I have a 1 over r here, which kills one of the powers of r here. I also have a 1 over r here, which kills the other power of r. So I had r squared, cancels 1r, and the other r. So what I'm left with is integral from 0 to infinity dr times the modulation that's left. I have e to the minus I qr minus e to the plus I qr times e to the minus mu r. G over h bar squared q 0 to infinity. Yes. Okay. So far, so good. So this is mg over I h bar squared q integral from 0 to infinity. If I just combine the exponentials, I get e to the minus mu minus I q r minus e to the minus mu. Oh, this one was plus minus I q r. Each one of these is a simple exponential. Each one of them I can safely integrate. So what I get is F equals mg over I h bar squared q. So I do the integration. I've got two different terms. In the first term, I get minus 1 over mu plus IQ times the value of the exponential at the upper limit, which thankfully, because of that Yukawa damping, that factor of mu up here, that safely goes to 0 when r goes to infinity. 0 minus, and then at the lower limit, if r is equal to 0, the exponential is just 1. Minus, in the same way I have the second term, minus 1 over mu minus IQ. Upper limit goes to 0, lower limit goes to 1. So I got a whole bunch of minus signs that I should clean up. So this is positive, and then this is negative overall. Mg over I h bar squared q. I have 1 over mu plus IQ minus 1 over mu minus IQ. Just some simple algebra, just got to put them over a common denominator. The common denominator is mu squared plus q squared. And in the numerator, I have mu minus IQ minus mu plus IQ. The mu's cancel. And I get minus 2IQ over mu squared plus q squared. So at the end of the day, this gives me F equals minus IGM over h bar squared q. From the integral, we got minus 2IQ over q squared plus mu squared. Minus I and minus I gives me -1. Yes, I had a 1 over I and an I upstairs, so I get -2 GM. Q cancels the Q downstairs over H bar squared, and then the real dependence on this, the important part, is 1 over Q squared plus mu squared. This is F of Q. What happened to theta and phi? I thought this was supposed to give me F of theta and phi. Where are they?
You already integrated over them?
Okay, fair. I integrated over the theta and phi associated with the position vector R. What happened to the theta and phi of the momentum vector of the outgoing particle? This is supposed to tell me what direction the outgoing wave is going. Where is that dependence in this expression?
Radial? Is there a symmetry over the theta and phi?
There's a radial component to it, but there is also angular structure in this expression.
In Q squared.
It's in Q squared, yes. Q squared contains angular information. H bar squared Q squared is 4 PF squared sine squared theta over 2. That is your angular information. So it does not look like there is angular information contained here, but there is because it knows about how much momentum you absorb. Depending on how much momentum you absorb from the target changes the deflection angle. So this is F of theta because it depends on Q squared. Why does it not depend on phi? Because the potential that I started off with was spherically symmetric. The Yukawa potential itself only depended on R. There was no XY dependence at all. The fact that it depends on theta comes from how much momentum it absorbs, not which direction it's going. So in general, if you have a spherically symmetric potential, V of R, you will always get something that depends only on the magnitude of Q, which means it depends only on the scattering angle theta and not on the azimuthal angle phi. Okay, so this was our answer for the Yukawa potential. If you are given under extreme pressure a scattering theory problem on an exam from me or a comprehensive exam, this is all you have to do. The actual work is in computing the Fourier transform. This Fourier transform was pretty straightforward. Elementary techniques were enough to do it. Some potentials are nastier and you have to work harder to get the Fourier transform out of it. Okay, so this was for the Yukawa potential. What does that give you for the cross section? And what does it look like if I compare the Yukawa potential versus the Coulomb potential? So the cross section, the sigma d omega is just absolute value of F squared. So I get a whole bunch of constants out front, 4 G squared M squared over H bar to the 4th, and the business end of it is Q squared plus mu squared squared. This, of course, contains a dependence on the angle. So this is 4 G squared M squared over H bar to the 4th. This is 1 over Q squared. Here, let me pull in the factors of H bar squared. So H bar squared Q squared, we said was 4 PF squared sine squared theta over 2 plus H bar squared mu squared squared. So this is the answer for the Yukawa potential, which contains a mass mu defining the range of the interaction. If I take mu goes to 0, then I just get 1 over sine to the 4th of theta over 2.
Where did that H bar to the 4th come from? The last one?
So I started off with 1 over H bar squared at the amplitude level. I squared it so I had 1 over H bar to the 4th. And then I didn't erase this from here. Thank you. I pull in the H bar to the 4th into the parentheses here. So for the case of the Coulomb potential, let me put them side by side so we can compare. Yukawa, we got the sigma d omega is 4gm squared, yeah, over 4 momentum squared sine squared theta over 2 plus H bar squared mu squared squared the Coulomb potential. D sigma d omega will just give me, let's see, I get 4 over 16, so I'm going to get T squared M squared over 4 PF squared 1 over sine to the 4th theta over 2. This goes by the name of the Rutherford cross section. Okay, so we plugged and chugged on the math. I want to take a few minutes to think about what the physics is telling us. Let me jump back to those plots now that we've done the math to get here. So this is what we started off with. We started off with the Yukawa potential, which contains an exponential damping factor associated with the range of the potential coming from the mass of the particle that's carrying the force. This is like the mass of the pion in nuclear physics. As opposed to the Coulomb potential, which is mediated by a massless photon. They have the same short distance behavior, but very different long range behavior. So what did we get? When we Fourier transformed these potentials, the Yukawa potential went like 1 over q squared plus mu squared. The Coulomb potential, if I kill the mu squared, just goes like 1 over q squared. That gives me functions that look like this. Notice now that they agree at large momentum and they disagree at low momentum. That's because of the mapping between position space and momentum space. Long distances or long wavelength in position space corresponds to short distances in coordinate space. So the fact that the two potentials agree at short distance means that they agree in the high momentum tail. They have the same content in terms of high momentum scattering. They have different content at low momentum. So you see the effect of the mass in the Yukawa potential is it takes that growth at low momentum and it cuts it off. You go to a finite maximum of low momentum modes for the Yukawa potential. On the other hand, the Coulomb potential of E and M blows up. You have an unlimited number of low momentum photons. That is an essential feature of E and M. And that is everywhere, and it causes all kinds of problems when you try to do scattering theory with relativity. There are all kinds of sick infinities that show up associated with the divergences of having infinite numbers of low momentum or collinear photons. So this is the physics of going from potential in position space to potentials in momentum space. What does that give us? If I take the cross sections that we calculated and I plot them, the difference is tremendous. D sigma d theta versus theta. So way down here is the Yukawa potential, and you see that the overall cross section for the Coulomb potential is blowing up. It is singular. If you try to calculate total rates for something like this, you will get infinite cross section. So you have to be careful about how to regulate these things, especially for the Coulomb potential. The Yukawa potential is nice and finite. You see, you get a little bump here. Both of these potentials have the same qualitative features. They are both maximum when theta is equal to 0. They both have a whole lot of low momentum modes. That means that your scattering is mostly in the forward direction. Your most probable scattering angle is 0. So most of the beam that comes in goes forward with very little bit of scattering because these potentials have lots of low momentum modes in. They do have some probability for hard scattering that comes out at pi radians, so back-to-back scattering, or pi over 2 radians. Overall normalization of these potentials will shift with the energy so that gap between them gets smaller and smaller when the energy of the beam gets larger. You can see here those features, if I plot it on a log scale, even more pronounced. So you see the sort of finite bump, the Lorentzian form of the Yukawa potential, and then you see the singular behavior of the Coulomb potential. I wanted to connect this to the physics of the infinite range and the 0 mass of the photon versus the finite mass and finite range of the pion in nuclear physics. Okay, any questions about this example? You have 2 problems like this on the homework where you were given a particular potential and you've got to repeat this exercise. Calculate the Fourier transform, plug it in, and get a cross section.
Was your way of saying that some Fourier transforms can be nasty, preparing us for the homework?
A little bit. So in the homework, one of the Fourier transforms you have is the Gaussian. That one is trivial. We've already done that in class. You do that Fourier transform by completing the square. The other one is one that I took from the comprehensive exams. That is the Fourier transform of the 1 over r squared potential. And that one, if you just try to do it as 1 over r squared, is nasty. The better thing to do is to do something similar to solving the Euclid potential, where you sort of treat it like you have a mass. Take your 1 over r squared and add a mu squared to it, or add an epsilon squared to it. Do the calculation with that finite regulator like mu, and then at the end of the day, you take mu goes to 0. So those are things that are spelled out in the hints on the homework on how to do that particular problem. On the comprehensive exam that I took it from, there were no such hints. So be prepared that you may have to deal with Fourier transforms like that on the fly. And if you see some sick infinities like that where your Fourier transform is not behaving properly, there are ways to regulate it and then take the limit as it goes to 0 at the end. So if we have enough time today, we will get to another example of that shortly when we discuss Green's functions.
Okay.
Okay. Any other questions before we continue on? Okay. So let me say a few words about how to go beyond the Born approximation using the time evolution operator that we've already discussed. For various reasons, that is not the approach that we will use to go beyond the Born approximation today, but it can work, and it introduces some important terminology that you may need to know. So beyond the Born approximation, using the time evolution operator. So one thing that you can do to try and describe scattering theory is to describe it as the time evolution of an incoming momentum state into an outgoing momentum state. So I can describe the scattering process as starting off in a momentum state P initial, time evolving it with the dress time evolution operator to plus infinity starting from minus infinity, and then ask what its overlap is on a particular momentum state P final. This describes exactly the same kind of process. This object, which is just the matrix element of the infinite time evolution operator between initial momentum and final momentum, is called the S matrix. This is the scattering matrix or the S matrix. In principle, if you can determine the S matrix, you can determine everything. And we already know how to do perturbation theory for the time evolution operator. So that's an appealing way to go about it. We know that the time evolution operator U of T and T naught is the bare time evolution operator minus T naught minus I over H bar integral dt prime from T naught to T, bare time evolution to T from T prime, the potential V that's being inserted at that particular time, and then bare time evolution to T prime from T naught, plus higher orders. We know how to construct this entire series. So this is an appealing way to do it. If I take it and I sandwich it between momentum states, what I get is an S matrix, which is e to the minus I over H bar, E final times time. The bare propagation from P initial to P final is only non-zero if they are the same state. So I have a delta. Probably I should write this as a delta function, but for the moment I'm just going to write it schematically as a Kronecker delta. Sometimes this is also written as a 1 in this discussion. The important part is the part that contains the potential, minus I over H bar. If I pull out the initial and final energy phases, then I just get the time evolution that we discussed before, dt prime from T naught to T, the potential now sandwiched between states, P final, V initial, times e to the plus I over H bar, E final minus E initial T prime. And in principle, I can construct the entire series out of this. We discussed doing this by iterating an integral equation. So we talked about the first order and the second order correction to the propagator. And then I've got a phase at the end of the day, e to the plus I over H bar, E initial times T naught. So we know how to do this. If I can take this thing and correctly take limits with t going to infinity and t naught going to minus infinity, then I can calculate the time evolution operator. I can calculate the S matrix. A couple of awkward parts about this that we've already had to wrestle with a little bit. One of them is that these time-dependent phases at the beginning and the end make it really awkward to try and take the limit t going to plus and minus infinity. We can get around that by going to the interaction picture, where I move those phases into the S matrix. So awkward phases. So before we got around this by saying, screw it, let's just take the absolute value of this thing. If we want the full information on how to get the scattering amplitude, we can't do that. We need all of the phase information and can't just take overall absolute values. But you can move them to the left-hand side and write the interaction picture part of the S matrix. So that basically just absorbs these factors, plus I over H bar, E final times time, let's say U of t, t naught, initial e to the minus I over H bar, the initial times t naught. And you can see if I pull these inside the matrix element here, it looks like I have e to the I over H bar Hamiltonian, e to the minus I H bar Hamiltonian, which is how you get it out of the interaction picture. If I do this, now I can safely take the limit with t going to plus and minus infinity. The other thing is that I really don't care about this the trivial term where no scattering occurred. So usually one subtracts out the Kronecker delta piece here, and you write something like SFI interaction picture minus delta FI. Sometimes you also see it written as S minus 1. This is the part that actually contains scattering to it. If I write this expression, I have minus I over H bar integral dt prime, and now I can safely take the limit minus infinity to plus infinity. Potential, final, potential, the initial, e to the plus I over H bar e final minus the initial times t prime. And I can integrate this thing over t prime. In principle, this contains the whole higher order perturbation series, which we know how to calculate and have at least done the second term. Now you see the second part of the awkwardness. So before I go on, let me introduce the other piece of terminology. If I pull out the factor of I, this is usually defined as the T matrix. I didn't actually find a clear definition of what the T stands for, but in my head, I always thought of it as the transition matrix. This is the part that generates the actual scattering amplitude. And at the end of the day, what we get is that the scattering amplitude F of theta and phi is proportional to the T matrix. So one thing that you can do, an approach that does work, although it's very awkward to do it, is to use the perturbation series we've already constructed for the time evolution operator and use it to construct the T matrix. If you know the T matrix, then you know the scattering amplitude. The other part of why this is awkward and why we're not going to do it that way today is you see immediately if I start to integrate this thing from minus to plus infinity, I get a delta function. If I integrate this exponential from minus to plus infinity, I get a delta. And that delta function is awkward because then I have to square it. And then I have two delta functions together, which is a very bad infinity. There are ways to modulate that. There's more hand waving that you can do to put it under control. But ultimately, it's just awkward to have a delta function at the level of the amplitude and then have to square it and then pull out a delta function at the level of the cross section. So I do not want to do it this way for our purposes today. We will do a closely related method, which is the method of Green's functions, that is similar to deriving a propagator, but not a propagator in time. Instead, it's a propagator in space. So that will look very similar to this setup, but I wanted you to see the terminology of the S matrix, which is just time evolution between the initial momentum and final momentum state. and the T matrix. This is the language that we use to talk about scattering theory in general, especially in relativistic quantum field theories. Okay, any questions about this before we tackle Green's functions? Okay, before I do that, can you guys let me know, have you encountered Green's functions before in any of your other classes? Often this is something that you do in E&M.
We covered it in Dr. Encar's math methods.
Oh, you did it in math methods. Okay, fantastic.
Or that was over a year ago.
Gotcha. Did you guys who took it last semester do Green's functions in math methods?
Yes.
You did. Okay, great. Well, then hopefully some of this stuff will not be too unfamiliar to you. Let me know if I'm going too slow and maybe I can skip some of the pedagogy in the beginning. Okay, so instead, we will solve the time-independent Schrodinger equation perturbatively using the method of Green's functions. So we said you don't really need to do time-dependent theory in order to describe the scattering problem. You can do it as a boundary value problem for the time-independent Schrodinger equation. So that's the approach that we will take now. The time-independent Schrodinger equation in 3 dimensions is minus h bar squared over 2m Laplacian plus v of r times my wave function psi equals the energy, let's call that h bar squared k squared over 2m psi. We're looking for the wave-like or positive energy solutions. So let's move around the potential here a little bit. So I'm going to move this term to the left-hand side, and I'm going to cancel out factors of 2m and h bar squared. So let's see. Let's move this term across. So on the right-hand side, I will write this as Laplacian plus k squared, acting on the wave function psi equals 2m over h bar squared v of r psi of r. Right, so this is the equation that we want to solve, and we would like to do it order by order or perturbatively in the potential. All right, so the thing that will allow us to do this is the method of Green's functions. So this is highly analogous to what you do in E&M. If you know how a point charge produces a potential, then I can write down any potential as coming from a distribution of charges. So if I know the potential of a point charge is 1 over r, then I know that if I have a charge density rho of r, then I can write any potential as an integral of rho of r divided by 1 over r minus r prime. So CF in E&M, you have something like a point charge whose potential is phi of r equals 1 over r in appropriate units. And that means that if I have a continuous distribution, that I can write phi of r is an integral over all possible sources d3 r prime, charge density at r prime, 1 over r minus r prime. So knowing how a point charge behaves is tantamount to knowing how all charge distributions behave. This is a general formulation of how to attack linear differential equations. For a linear differential equation, knowledge of how it responds a point source, something like three-dimensional delta function of r minus r prime, is tantamount to knowing the exact solution. So the idea is, if I have a differential equation that I want to solve, can I solve it for the response to a point disturbance? And if I know the response to a point source, then I can use that to construct the solution in general. That is what a Green's function is. That is the response of your DPQ to a point source. This is also why it's sometimes referred to as the propagator. But this is really like a spatial propagator, not a time-like propagator. It says, if I have a point-like disturbance, how does that information propagate out in the solution to my differential equation? So you are taking a source here and you are propagating it from point r prime to point r. So all of this is a way of motivating what I mean when I write this equation down. The definition of a Green's function for this equation is one such that the Laplacian plus k squared on it, Green's function which depends on r and r prime, is a delta function. This is the definition of the Green's function for our particular differential equation. I should also be careful now that there are a couple of position variables rolling around. This gradient, or Laplacian, is the Laplacian with respect to r, with r prime held fixed. So how do you do this? What is the analog of saying, if I know the potential of a point charge, I know the potential for everything? If I have a function like this, I should be able to construct the general solution to my differential equation. So how does this help? If I know G. If I know G, I can go back to my original equation. Laplacian plus k squared psi equals, what were my constants? 2m over h bar squared v of r psi of r. I can introduce the Green's function by artificially starting with an integration over space and a delta function on the right-hand side. d3r prime 2m over h bar squared v of r prime psi of r prime delta function r minus r prime. If I have a Green's function, then I can write this delta function as what I get when this operator acts on the Green's function. So I can write this right-hand side as Laplacian plus k squared acting on d3r prime 2m over h bar squared v of r prime psi of r prime Green's function or propagator of r and r prime. Now on the left-hand side, I have that operator acting on psi. On the right-hand side, I have the same operator acting on something involving the Green's function. If I put them together, then that operator acting on the combination gives me 0. So this tells me Laplacian plus k squared acting on the whole combination, psi minus 2m over h bar squared, integral d3r prime, v of r prime, psi of r prime, Green's function or propagator of r and r prime. That operator acting on this combination is equal to 0. So that means whatever this object in brackets is, it must correspond to a solution of the free particle equation. So this must be a solution psi naught when the potential is 0. So therefore, this object is equal to psi naught, solution to the free particle case with v equals 0. because this means del squared plus k squared psi naught is equal to 0. That's the homogeneous equation. So this is a way of building solutions to the inhomogeneous differential equation with some potential v out of the solution to the homogeneous equation, which you know, and then constructing it order by order in the source. So this lets me ultimately solve for the general solution psi of r equals the homogeneous solution psi naught of r plus 2m over h bar squared d3r prime v of r prime psi of r prime propagator to r from r prime. Make sure all my factors are good. Yes. So this is very similar to what we did when we constructed the dressed time evolution operator. Notice that this is an integral equation. I have psi on the left-hand side, the full solution here. Psi is also sitting inside the integrand here. So this is not an explicit solution, this is an integral equation that lets you turn the crank and calculate the full solution iteratively. And this is where the perturbation series comes from, exactly the same way as what we did for the time evolution operator. I take psi equals free particle plus a correction proportional to the potential. So in this side, now I again plug in psi naught plus a correction. And that correction involves psi squared. And it has two insertions of the potential. And if I keep chugging the integral equation over and over again, I calculate one order higher and higher in the potential every time. So if I explicitly write down the iteration for the first one or two instances, what I get is the full solution psi of r is the free particle psi naught of r. The first order correction is one propagator and one potential, 2m over h bar squared, d3 r prime, v of r prime, psi naught of r prime, the free particle at that point, times the propagator, g of r and r prime, plus a second order correction where now I've shoved the integral equation twice, 2m over h bar squared squared. Now I have two integrals, d3r prime, d3r double prime. And I have potential at, let me see how I'm calling this. Let me write it in this order. Propagator to r from r double prime. Potential at r double prime. Propagator to r double prime from r prime. Potential at r prime. Psi naught of r prime. So you can see how this starts to look the same way that we talked about the time evolution operator. You have the bare solution at a point, it hits the potential, and then it propagates. Then it hits the potential again. Then it propagates to where you finally measure it at point R. So you can describe this solution diagrammatically. So it would be something like my wave function at point R equals, I don't know, just the bare wave function psi naught at point R, plus a correction where your wave function started at some point and then it hit the potential. Psi naught at point R prime, potential at point R prime, and then it propagates through space to where you finally measure it at point R. This is the propagator given by the Green's function. Plus two insertions. You start off with the wave function psi naught, it immediately gets hit by the potential, it propagates for a bit, it gets hit again, it propagates a bit, and then you measure it at point R. Yes, that's how I said it. One propagator, second propagator, and so on. This sort of representation I'm drawing here is not like standard diagrams. I'm trying to give you something visually to wrap your head around about what this looks like. We will get a much simpler picture about how to diagrammatically represent the perturbation series in terms of Green's functions when we go to momentum space. Okay, this is what a Green's function is. This is how, if you solve for the Green's function for a differential equation, you can use it to construct the solution to that equation order by order in perturbation theory. Now we have to actually start the work, which is to find the Green's function for our particular differential equation. Is everybody clear on this part? What a Green's function is and how to use it? How much of this had you encountered before in the math methods classes? Maybe I'm presenting it a different way here. How much of this is already familiar?
Yeah. Anghar presented the Green's function as a kind of reverse operator.
Yeah, that's exactly right. So when we wrote it down as operator times Green's function equals delta function, yeah, that's equivalent to saying that your Green's function is sort of the operator inverse. Quote unquote. We'll find a way to put this on a more solid footing when we go to Fourier transform it. You can't really like divide by the Laplacian. But if I Fourier transform this into momentum space where this is an algebraic equation, I can. So yeah, this is equivalent to saying that your the Green's function or the propagator is the inverse of the operator. So I try to use the term propagator as much as possible because that has physical meaning to me. Whereas if I just say Green's function, it sounds like some abstract mathematical concept. Okay, so how do we find our particular Green's function? So the object that we want to find is a solution such that del squared plus k squared Green's function of r and r prime is a delta function, three-dimensional delta function of r minus r prime. And this operator acts on the position r. So the way that we will do it, as I've hinted several times now, is by Fourier transform. So one thing that we can do to make our lives a little easier is to say the right-hand side is translationally invariant. So I expect my solution for G to also be translationally invariant. So we expect that this Green's function will be a function only of the difference, r minus r prime. If my differential equation had some r dependency in here explicitly, then maybe that wouldn't be true. It wouldn't be translationally invariant. But since it is translationally invariant, it seems like it should only depend on the difference. And translationally invariant systems are best solved in momentum space. So if I write it in terms of that relative coordinates, then I can say del squared r plus k squared g of r equals delta 3 of r. And now I don't have to worry about which coordinate I'm talking about anymore, because there's only one. So let's solve this by Fourier transform. My three-dimensional delta function, delta 3 of r, I can write as the three-dimensional Fourier transform d3 cubed over 2 pi cubed e to the plus I q dot r. This is the convention that I want. Yes. And so likewise, I define my Fourier transform g of r defined to be d3q over 2 pi cubed e to the plus I q dot r times its Fourier image g tilde of q. So when I go to momentum space, on the left-hand side, I have del squared plus k squared acting on integral d3q over 2 pi cubed e to the I q dot r g of q equals integral d3q over 2 pi cubed e to the I q dot r 1, if you like. The virtue of all of this is that now in momentum space, del squared only hits the Fourier phase factor. So I get minus q squared from when this acts on. So what this gives me is integral d3q over 2 pi cubed, k squared minus q squared, g of q, e to the I q dot r equals d3q over 2 pi cubed, e to the I q dot r, 1. Or if I subtract the right-hand side over to the left, this says integral d3q over 2 pi cubed, k squared minus q squared, plus k squared minus q squared g tilde minus 1. E to the I q dot r equals 0. So now I solve this equation in momentum space and I get g tilde of q is 1 over k squared plus q squared. For the case when k squared is not equal to q squared. That's the only problem with this. So I left this bit in the corner there. Jacob made a comment about in math methods, Dr. Engelhardt presents the Green's function as the inverse of the operator. This is the sense in which it is the inverse of the operator. I can't meaningfully write 1 over the Laplacian, but I can in momentum space write 1 over k squared, not plus q squared minus q squared. I can in momentum space write it out algebraically. So this is what it means. It's no accident that it's 1 over the Fourier transform of this thing. So this is a very nice solution as long as the Q that you're talking about, the Fourier mode, does not exactly correspond to this k squared, which is the energy of the solution. And so recall, energy was h bar squared k squared over 2m. That's what k is. So when Q is exactly the right Q, that this describes the energy of the particle, this thing goes to infinity. It's not well defined. So this is another example of a Fourier transform that is not clean. To handle this, we need to regulate this. So we need to use a regulator. In this case, I mean some epsilon, which I'm taking to be a positive number, that I take the limit goes to 0 at the end. It's also important to note at this point that there is not one unique way to regulate this thing. I'm going to basically take this denominator and add something proportional to epsilon to it. There is a non-unique way to do that. And depending on what way you choose, that will determine what kind of solution you get. The choice that we're about to make now is the one that will lead us to have an outgoing spherical wave. The choice of how to do it is non-unique. We will pick the one leading to an outgoing wave. So this is an exercise which is similar to one of the Fourier transforms that you need to do on the homework, the one that I pulled from the comprehensive exam. So what I will do is I will modify this and I will add I epsilon to the denominator. T of Q is 1 over k squared minus q squared plus I epsilon. The only purpose of this epsilon here is to shift the singularity where k squared equals q squared off the real axis. This will allow us to do the inverse transform by contour integration. G of R is integral d3q over 2 pi cubed e to the plus I q dot r 1 over k squared minus q squared plus I epsilon. Without the I epsilon, this integral goes to infinity on the real axis. But this choice moves that singularity off into the complex plane. And so that will tell me if I close the contour above, if I close the contour below, do I get a residue or do I not? So the trick is I'm going to identify the poles of this propagator to order epsilon. Epsilon is an infinitesimal thing, which means I don't care about epsilon squared. Don't care about epsilon squared. Don't care about constant factors. I'm not going to distinguish between epsilon and 2 epsilon and epsilon times k. I only care about is it a positive number or a negative number so that I know is the pole above or is the pole below. So with that in mind, I'm going to write this denominator as k plus q plus I epsilon, k minus q plus I epsilon. To order epsilon, the linear term is k squared minus q squared and an I epsilon that goes with it times a positive number. The correction to this is order epsilon squared, but I don't care. The cross term from this thing involves a factor of 2k, but I don't care about the 2k. That's just some positive number. All I care about is this in the upper half plane or in the lower half plane? Set. I need to make that a minus. I've got something inconsistent in my notes here. I think plus is the one that I want here. We'll find out in a second. I think it's plus. Okay, so the point of this is that I can do the Fourier transform now by contour integration. So I'm going to write that d3q as integral 0 to infinity dq times q squared, integral minus 1 to plus 1 d cosine theta, integral from 0 to 2 pi d phi. And I'm going to write e to the I q dot r as e to the I qr cosine theta, just like the example that we did earlier with the Fourier transform of the Euclid potential. So the d phi integral trivially gives me a factor of 2 pi. The d cosine theta integral gives me something similar to what we did before. The contour integration is only going to come in the last step when we do the radial integral over q. So I get T of r equals, I had 1 over 2 pi cubed, I get another factor of 2 pi from the phi integral, so I have 1 over 2 pi squared. Integral from 0 to infinity dq times q squared from the phi integration. When I integrate the theta integration, when I integrate d cosine theta, I get 1 over IQR e to the plus IQR minus e to the minus IQR. Times 1 over this denominator, k squared minus q squared plus I epsilon. So I get g of r is equal to, 1 over 2 pi squared, integral from 0 to infinity dq times q squared. I have 1 over IQR e to the IQR minus e to the minus IQR 1 over k squared minus q squared plus I epsilon. So 1 over q cancels one of those factors. Yes, so I have 1 over IR 1 over 2 pi squared. Integral from 0 to infinity dq q e to the IQR minus e to the minus IQR k squared minus q squared plus I epsilon. I would like to be able to do this last integral by contour integration, but I can't in this form because the integral only goes from 0 to infinity. To do the contour integration, I need an integral that goes from minus to plus infinity. And so for that, I look at these two terms. They differ by a minus sign, and q goes to minus q. If I take q goes to minus q in that second term, here, q goes to minus q. This p stays the same. This e to the minus IQR becomes plus, e to the plus IQR, rather. So when I take q to minus q, I get a sign change here. I get a sign change in dq. And I have to flip the limits of integration. So when I do this, I get IR 2 pi squared integral minus infinity to plus infinity. Q e to the I QR k squared minus q squared plus x. So I've taken that second term, and by taking q to negative q, I've combined it with the first one. Now I've got a nicely behaved integral from minus to plus infinity that looks amenable to contour integration. So now's the part where I need to know where the poles are. So I have convinced myself that what I had is plus I epsilon in both cases. Yes, because then the cross term gives me k plus q plus k minus q. So the overall factor is 2k, which is a positive number. So how does the contour integration look for this? So my contour integration is running along the real axis. Q goes from minus infinity to plus infinity. The poles of this propagator, the poles of the denominator here, are at q equals negative k minus I epsilon, and q equals positive k plus I epsilon. So the two poles are located here. One here at k and plus I epsilon, and the other one is at negative k minus epsilon. Now I know when I close my contour one way versus the other, which pole I pick up. This is the part where choosing plus I epsilon mattered. That will tell me when I close the contour above that this is the pole that I get, or I have positive k, and not this one which has negative k. Okay, so how do I do it by contour integration? I have e to the IQR, which controls the asymptotics. Do I close this integral above or below?
Above.
Above, because this is e to the plus IQR. If q becomes imaginary, if I have IQ, then this becomes a decaying exponential, e to the minus absolute value of q. So this is exponentially decaying up, it is exponentially exploding down. So you have convergence enough to close the contour above and collect this residue. So that if I have, let's say, the imaginary part of q is positive, then that means that my e to the IQR becomes e to the minus absolute value of QR. And that means that this is a convergent decaying exponential. When I close it above, I get a factor 2 pi I, and I collect the residues. So I get g of r is 1 over IR, 2 pi squared. I get a factor of 2 pi I from closing it above, and I have to plug in the residue, this expression, when q is equal to k plus I epsilon. So up in the exponential, right, so I had 3 different places where q occurs. So I have here in the exponential where I've got to plug it in, here in the prefactor where I've got to plug it in. This one is the pole that I picked up, and so I've got to plug it in here. So when I do that, I have q equals k plus I epsilon. I have e to the I k plus I epsilon r. When I plug it into that other factor in the denominator, I get 1 over 2k plus I epsilon. And it may not be obvious from the way that it's written here, but I also get a minus sign because the formula for the residue has q minus the pole value. So because we had minus q here, and q is the thing we're picking up the residue of, there's a minus sign. So recall in Cauchy's integral formula that your, what is it, integral, closed loop integral dc of f of z over its z minus z naught. This is what I'm talking about here. That gives you 2 pi I f of z naught. Here we didn't have z minus z naught, we had z naught minus z. That's where this minus sign comes from. Okay, finally, we plug it all back in. 2 pi cancels one of the 2 pi's. I cancels the I have 1 over r, and now I can safely take epsilon to 0. All I needed it for was to know where the poles were so I could complete the contour. Now I can put epsilon to 0 and forget about it. So I have 1 over 2 pi r from the prefactor. From the rest of this stuff, I have minus k e to the I k r divided by 2k. So at the end of the day, I get minus 1 over 4 pi e to the I k r over k r. No, I cancel the k's. There, that's it. So we have found the Green's function. It is a spherical wave, e to the I k r over r with a prefactor minus 1 over 4 pi. The particular choice that we made with the plus I epsilon that put this pole in the upper half plane led us to get k plus k for the value. That's this solution, which is the outgoing wave. So the choice plus I epsilon for the regulator led to e to the plus I k r, which is the outgoing spherical wave that we want. If we had made the opposite choice, if we had taken minus I epsilon or something else, then maybe this pole is the one that would have been up and this one would have been down. Or maybe they would have both been up, or maybe they would have both been down. Depending on how you regulate it, you can move those poles in different ways. But this is the solution that we want physically to give us the outgoing spherical wave. All right, I'm already over time, so let's stop here. Now that we have found the Green's function, the next step will be to plug it back in and construct the iterative solution explicitly, and then take the long distance asymptotics to extract the scattering moment. Any questions or comments? Okay, then next time we will continue this, and we will begin discussing scattering amplitudes, phase shifts, and partial waves. Thank you guys very much. Have a nice weekend.
Thank you.
Dr. Seaver, do you have a chance to chat about some of the homeworks later today?
Yes, I can't do it right this second, but sometime afternoon, I think. I'll be home and my son will be running around going crazy, but I can certainly chat about things there.
Perfect. That would be great. Thank you.
Sure, sounds good.